Thank you. Ryan, are you going back to the department after this?
Yeah.
Can you take this back for me? It's actually belongs to George Grover.
Okay.
So maybe I should return
Where do you want me
it.
to put it?
Can you keep it in the lab?
Yeah.
Thanks. I'm trying to think of someplace safe because George is probably long gone.
Sure.
So let me know. I had a couple good feedback about the lectures, how to make them easier to navigate, and I have a tendency to move. Actually, I wrote a paper on occupational energy expenditure, and teacher was ranked as a moderately active profession. So I don't think anyone's ever seen me because I'm probably overly active in the classroom. So I'm going to try very hard not to go over there and start pointing with my hands and doing some of these. And I'm going to try to stay right here because the mouse itself can be used to point at things. But if you see me starting to go there, they'll make a little motion and bring me back to here so that it's recorded. Otherwise, where I'm pointing at won't be recorded on here. The second thing is somebody asked me to make sure that I order all in order. So I can't, I tried on the playlist to do it. It seems like a pain to move them in the order that I want to. So I'm going to call it video 1, video 2, and with the date so that you can click on the number of the video. But keep them coming because my undergrads are very, very quiet about what they like and don't like. So it's easier to get feedback from you and implement it and then apply it and stick it on them. So a number of questions were about the last class, how we're going to use the book. So Montclair State, our graduate program, is a very unique graduate program in some ways. It's not we're not at Rutgers trying to get a PhD in math. So many people have different reasons here of why they're here. Some of you are high school teachers and getting your master's and you want to do mathematics as your master's. Some of you would like to go on to a PhD program. Some of you really disliked abstract algebra as an undergrad and are checking the box here. Some of you are an undergrad who actually want to do more because you love this stuff. So we have a huge breadth of variation in the class of the goals that people have. So choosing the book, if there's been one class I've taught more than any other at Montclair State, which there isn't really because I tend to go to different classes every semester, it's abstract algebra. So I've been thinking about this for a long time. There isn't really a good book for what we want. You're not an undergrad. But, well, maybe one of you. So, you're a graduate student, so your frontal lobes are more fully formed than an undergrad's. Yet, you have different reasons of why you want to be in here. So the answer is not to select a book that's harder than the undergrad book because some people didn't have a good undergrad class. So this book I'm using in class as a guide to order the topics and to select some of the homework problems from. And the definitions are definitely there. But, and the homework problems for the most part will be from the book, but not all. We'll spend more time in the class thinking about the material more deeply. So I'm pulling out other examples for you to look at, to think about. We're going to do more in-class work so you can explore more items. And I'd like to use a more discovery approach because as I taught it over the years, what I've realized is that when I get my students to compute in the graduate courses, first they're more onto it than the undergrad students, and they're ready for it. But it helps them learn so much more, just to see some of these things computed out and see the examples or why something's working. It's almost like you can take even the most disgusting undergrad class and kind of tie things together. So that's one of the things I'd like to do. Now, in the past, I've been making up problems for a discovery type of approach. And so I have to kind of think of all of that on my own. But I did find a fantastic book at the joint math meetings where it had some of the ideas that I already was using, but it has it all in a book form. But I was hesitant to use that as a main book. So I'm still kind of using some of what they have there and some of what I have myself. But whatever it is, it's going to be more than just the textbook. The textbook's almost like a skeleton. What the course is not, some of you are really happy that I was using this book because you told me I used that book as an undergrad. It's not a repeat of your undergrad book. That won't be the case. So I'm not going to go through the book and just regurgitate for you what's in the book on the board. And it's also not a faster version of an undergrad class. I'm really against this. I talk to my son a lot about this because he sees kids being moved ahead You know, he's 1 grade ahead, somebody got moved 2 grades ahead. Like, stop, slow down. It's not about running as fast as you can through your math courses. It's about smelling the roses and enjoying your time there. So, just holding him back and making him understand that harder doesn't mean faster. It's not the same thing. You can actually take something very simple. You can take stuff from elementary school mathematics and make it, start thinking about it more deeply. So it's not, definitely not, we're not going to go through this book a lot faster than you did in your undergrad class. That's not the approach either. Keep in mind, as you're in here, there's quite a mix in here. There's a student here who absolutely loves abstract algebra and probably should write a thesis on the topic. So she should see me after class. And there's others of you that had a really strong undergrad class. And there's some of you that are checking the box. We're all in this class together, and what I've seen in the past is my students in my classes end up knowing each other very well, and they end up kind of feeding off of each other, and everybody comes to the same place. So you might find that you didn't understand anything from your undergrad abstract class, and all of a sudden you're remembering some things from there, like, oh, that's what they meant. Or here's another example that my undergrad teacher showed me. I had no idea what that meant back then. So even if you had a poor undergrad class, you might find yourself actually pulling some of that material and offering new innovative ideas in here. So we're all kind of in this together, and I've seen it done before. I've seen it in the other abstract class that I had before. Everybody kind of came to the same page, where people who really liked it were showering their enthusiasm on everybody else, and people who didn't like it so much, they ended up liking it at the end of the semester. So it'll happen. Goal. Are there any questions about how I plan to use the book? I think I covered it all. I think undergrad too, I want to mention, like, you teach the grad class and you teach the undergrad class. I have the luxury of teaching both. The undergrad class is so different than the grad class, and I think because the undergrad class, many of the students walk into the undergrad abstract algebra with the mindset of they know what math is. It's calculus. It's computations and it's calculus. And then you try to get students who are 20 years old trying to slow down, think about things deeply, write more. Of course, mathematics is not about writing. So, they have these preconceived notions in their head. I spent so much time in the undergrad class trying to wipe away those preconceived notions and hoping that they won't walk out of that class saying, I really, really hate this. So this is a kind of a balance. I don't find that with the graduate courses. It's almost like even if somebody didn't have a good experience in their undergrad classes, they'll come to the grad class with a much more open mind. So it's just a different population of students. And you're all grad students. So I would expect that even if you are trying to hate it, you're going to end up having a different appreciation just because you're a little bit older. Thank God, I hope no one judges me for what I've done when I was 20 years old. So it's different. So I hope that gives you a little bit more of an idea, but you'll see as we move on. I take a little time to get used to, but you'll see as we move on, it's going to be okay, and we'll all balance out at the end. Any questions? By the way, I usually get what I want. So I want to start off today with a definition of group. Some of you had mentioned in your info sheets you wanted a better understanding of groups. This is it. This is the class that's going to do it. A group. So in undergraduate classes, I think one of the problems is that in the junior and senior year, you get all these classes at once. And you have all these objects that you're studying. In linear algebra, you're studying matrices. Abstract algebra, you're in this land of groups. Some of them look like something familiar. Some of them don't look like something familiar. So what are all these things? And in undergrad courses, I always tell students to think about what they're looking at. Vector, what does that mean? Have an image of a vector in your head. It's not a point, it's a vector. Matrix, it's a matrix. Group, you have to think and stretch your mind now in different ways and say, group is not just integers. A group could be, now you know, braids. So you have to have some examples that stretch your mind. But in essence, a group is a set. It's a box of objects. Want weird objects? Braids. Think of the braids all being formed into a set, 2-string braids. And it has a binary operation, star, which we defined last time, that satisfies 3 things. And I made this like a checklist, because if you have to prove something is a group, you go down the list and check off. First, there exists an element in the group, we label that E, such that it leaves elements unchanged under binary operations. So it behaves like a 0 for addition, or it behaves like a 1 for multiplication. This element is called the identity element. The second property is what we call the associative law. I think books have changed these days, but when I was growing up, way up north, we always started out with set theory in our classes in high school, and I think in 7th and 8th grade we started with set theory all the time. I don't think that's the way things are done anymore, but we always had the list of rules: associative rule, distributive rule, and commutative. Some algebraists went nuts and changed the whole curriculum, so it started off this way. But associative law was one of the things on that list, and it basically says that the order of how you operate doesn't matter. You could star B and C first and then star A next, or you could star A and B first and star C next. And don't freak out if you're taking notes. I just copied and pasted everything. The third rule is that you have an identity element. I realized, and you have an inverse element. You have something for every element A in the group. There's another element, call it S, that you can star by that takes you back to the identity. And this element's called an inverse. And when you're writing proofs, I discourage using A inverse just because it makes you think of 1 over A, which is something to do with multiplication. So usually if you had more of a weak undergrad abstract class, I would start off with always using this definition and not using symbols. But as I went on and developed the notes, I started using the symbol, and I realized sometimes I just need the symbol because I need to identify the inverse with the original element A. And that's it. That's what a group is. So this is mathematics. This is how we operate. We start with definitions. We're very rigorous and precise about them. And there's no shred of doubt in anyone's mind at the end of the day. That's why we call ourselves the pure of all the pure sciences. We're the purest of them all. Did you see that T-shirt at the joint math meetings that said that I'm not pure? I got one for Dr. Forgeston. So there's a number of standard examples on page 39 and 40 in your book. So I suggest you review those examples. The 2-string braids that I showed you the other day, they do form a group. I'll formalize that in a second, but I'd like you to begin right now looking at what may be the inverse and may be the identity for a group. So if you recall for braids, this is an example of a braid. And this was an example of another braid. I'm just going to put the same one underneath it. And we did this attachment business where we removed the rod in the center and just attached the strings. And you would want to know what kind of attachment would leave this unchanged. That would be your identity, right? And the next thing you'd want to know is what kind of attachment could you make to a braid to bring it back to the identity. So all I want you to do is play around by drawing pictures at your desk in a group of 3. Let me see if I wrote this up. Yeah, I did. So just play around and take a guess. And so what I like to do is work in groups of 3. I taught at West Point. They made such a big deal about groups of 3. It's a military, right? If they say a group of 3, and they say strongly suggest, they mean do it or else. So no less than 2. Don't work by yourself, and don't work in more than a group of 3 because then we get the smoking and joking factor falling in. So then turn in your work on separate sheets of paper at the end. So I need everybody's name in your group, first and last right now. I'll get to know your name soon. And only one submission per group. So pick whoever has the neatest handwriting, preferably, to be the person who scribes everything down.